Welcome back. Let's finish the chapter Pointers and Arrays by explaining the last two sections, which are arrays of pointers and void pointers. You can see and watch the explanation of the previous sections by going into the description box of this video and clicking on the playlist link. Also, in the description box, you can see the outline of this video minute by minute. In this chapter, we have seen pointers, we have seen arrays, and we have seen the close relationship between both. We must say now that C supports also multidimensional arrays. So what about them? The simplest form of the multidimensional array is a two-dimensional array. A two-dimensional array is an array of one-dimensional arrays. So it is an array of arrays. The general form declaration will be the type, the array name, the dimension 2, and the dimension 9. And you can generalize this to the multidimensional arrays of whatever dimension you want. So let's take an example. If we declare int t34, this means that t is an array of 3 elements where each element is an array of 4 integers. So t is an array of 3 elements. Each element is a int bracket 4. In a function parameter list, and because functions can be compiled separately, you must denote all but one dimension of a multiple dimension array. So if you want to pass t to a function called a function, you will pass it as this, int t brackets, empty brackets and brackets with 4. Of course, the empty brackets, we all agree that they can be replaced by a star. And of course, if you don't want your function to access any forbidden memory, you will pass this missing dimension as a second parameter, as we have used to do in the one-dimensional arrays. And you already know that arrays are referenced through pointers, so there are multiple ways to declare and access two-dimensional arrays. We will see this now, and it will become more relevant when you are dealing with an array of strings in particular, not an array of any other arrays. So let's proceed by example, and let's consider this program which fills an two-dimensional array with even numbers starting from 2. So regardless of this nice expression, depending on the indexes I and j to fill the even numbers, we are concerned now by double for loop needed in order to fill the array. So our concern is this for loop for I and for j in order to fill the elements t of I of j. So this is your regular way, and we will see how using pointers we can substitute this double loop with a simple loop, since an array is pointed to by a pointer. So let's consider this array and suppose for now that we filled it explicitly during the declaration, and let's see how it is represented in the memory. You might think that T is represented as a two-dimensional array, as we have seen in math. It is close enough to this representation, but T in fact looks more like this representation, where T is an array of 3 elements, each of which is an array of 4 elements. So in fact, in the memory, the elements of T are not on separate rows, but they are contiguous one after the other. So directly after the 8, there would be the integer holding 10. The elements are contiguous from 0 to 11 instead of from 0 to 3, 0 to 3, 0 to 3. So we can have a better way to iterate this array, since in reality it is a one-dimensional array. So whatever the dimension of multidimensional arrays, in reality they are 1D arrays. In order to use the pointer syntax, let us recall the equivalent syntaxes we have seen in the beginning of this chapter. Whenever I write p of I, it is exactly equivalent to the reference of p plus I, and whenever I write the address of p of I, it is exactly equivalent to p plus I simply. So let us use this recall to evaluate t of 1, 2. T of 1, 2, if you look here, this is t of 1 and second column, which is 14. Is this equivalent to what I have learned in pointer? Is this t dereference of t plus 1. Let me see, t plus 1, it is here. We dereference it. We become here inside this element. And then of 2, then again a plus 2, we will be in here plus 0, plus 1, plus 2. This is the plus 2. This address, we are here, and then we dereference to enter 14. So in the both cases, we will have 14, and this is true. The value of this expression is 14. Let us try now to evaluate this expression. Dereference of t1. So this is t, and this is t1. And if we dereference it, we will get the value 10. We will follow the arrow, the blue arrow, medium blue arrow. We will get the value 10. And this is true. Let us try to evaluate dereference t plus 2. So this is becoming a little bit complicated, but since we have the equivalent syntaxes, since we know how to dereference and follow an arrow, this is very, very easy. So t plus 2, this is t pointing here. So the value of t plus 2 using the pointer arithmetics, we advance 2 places. So it will be pointing t plus 2 is this address here, this corner. If we dereference it, we get this pointer. If we again dereference it, we will follow the light blue arrow to reach 18. Is this equal to t of 2 of 0? Yes, this is equal to t of 2 of 0. And lastly, let's try to evaluate dereference of t plus 2 plus 1. This is the same as t of 2, just like before, but not of 0, of 1. So we will dereference t plus 2 to get this light arrow, and then we dereference it and add 1, and then enter by dereferencing again. So this is the value 20. So this is very easy. We can now write pointer syntax in order to iterate two-dimensional arrays. So let's do it, and let's go back to our example to fill the 2D array, and let's change. We don't like the two nested loops here. We want one loop. So what do we do? Look how I changed the loop. I took a pointer p in which I put the dereference of t inside it. So I will begin here. The pointer will get this value, so he will get the address of the first element of the 1D array. And we will loop iterating using p. For p equal dereference t, I initialize a value to 1, p less than dereference t plus 12 places. I advance p and I advance the value, and at every time I dereference p and I put inside it double the value v. So I will put 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. This is how my beautiful loop has become. Of course, I could have also iterate the same way in order to display, but I chose not to in order for you to be convinced that this is the same array. You can iterate it in the same program using a one loop or two nested loops. So this is our fill2D array, and let's see what's next. So we have seen until now that a two-dimensional array is in fact an array of one-dimensional arrays. So the syntax int a brackets brackets is nothing but int star a brackets. In particular, let's see another generic syntax, which is int star a of 3, for example. It means a is an array of 3 elements, each of which is an integer star. So each element in A is a pointer to an integer. Let's continue and see what we are trying to show you here in this partial program. So I am declaring A, and I am declaring 3 one-dimensional arrays, x, y, and z, each of different lengths. So x holds 2 elements, y is an array of 3 integers, and z is an array of 4 integers. So this is the representation. A is an array of 3 integer pointers, and x, y, and z are arrays of integers. So what can I do with this? I can say a of 0 receives x. Yes, I can, because x is an int star, and a of 0, every element in a is an int star. So this assignment is permitted, and a now will copy the value that is inside x to its first element. So I copy here, paste here, and a of 0 will point also x of 0. The same goes for a of 1, in which I will copy y, and on a of 2, in which I will copy z. I have now this schema, and I can say that A is a jagged array. How? You can imagine, take only this part. This is its representation. A is a jagged array where each row does not hold the same columns as the other. If we want to do the same thing we did just a few minutes ago, I can printf the A1, 2. I go A1, column 2. It will be the element 5. Do I do the same in my real representation? Yes. A of 1, and then I follow the reference, and on column 2 I will reach the element 5. What about A of 0, 2? I go to A of 0 and I try to dereference and add 2 places. I will not find anything. The same here, A of 0, 2 does not exist, so it will give me a garbage value. If I run this, I will get any value. Let us do this, but after trying to print the last expression, print f dereference d, dereference of dereference a plus 2 plus 1, all dereferenced. So this is a of 2, 1. This is a plus 2. So we dereference it, and then a plus 1 and dereference to get the value 7, which is in fact a of 2, 1. So it will give me the value 7. Let's go and check this in the compiler. Try to run this in order to see what I will get. Of course, I get 5. I get any garbage value. It depends from one run to another. And then I get 7, and this is my execution. We have seen arrays of arrays, and in particular now we will see arrays of strings. So how we will represent this in C? We can implement an array of strings as a two-dimensional array of characters. So an array of elements where each element is an array of characters. Like this, for example, we have a names, not one name, many names, 120 names, each of which is an array of 50 characters, supposingly that a name would not exceed 50 characters. This representation of the array of strings has disadvantages. The most important one is that all the 120 strings will be of 50 characters long. Even Ava, which needs only 4 places for the E, V, A, and \0, will be reserved for her 50 places in the memory. So let's see an example in order to illustrate what we are talking about by reference to the Douglas Adams book, So Long and Thanks for the Fish. We will create an array of strings, and here, instead of declaring it as a double array, we will declare it as an array of char star, where char star are the C strings, the pointer to characters, and we have seen this in the beginning of the section strings versus arrays of characters. So we will initialize directly this array of strings. We will give all the strings, so it will be an array of size 1, 2, 3, 4 elements. Each element is a char star directly initialized, so each element is a constant. So we will put hello, goodbye, so long, thanks for the fish. You can see and notice that those strings don't have exactly the same size. They differ in sizes. And now if I want to print my strings using puts in order to check whether my strings have been successfully saved in the array of strings, I will get, of course, the hello, goodbye, so long each on a line because puts adds a new line after the string. And if I want to make sure how many bytes did I use in the memory, I will just print the unsigned long value, which is the size of x all divided by size of one character. So this is how many bytes, how many characters did I use in order to store x. It will print 32 with the backslash 0. So if you count all the letters, they are exactly 32 if we count also the backslash 0. What I was saying that this representation is better than the double array of characters. Suppose we take a double array of characters now and see what is the difference. The difference is that a double array of characters will be of at least the second dimension will be at least 24 characters in order to hold the longest string in this initialization. So we are obliged to put 24 or else we will trunk the last string. So we will keep all the others the same. We changed only from char star x brackets to char x brackets 24. We have seen previously that we can give all but one dimension because it is deduced from the number of elements given at the initialization. So we have an array of a char arrays of each of which is 24 characters. If we do this and we print the size of x over the size of char, it will sure be 96 bytes because we won't have a jagged array, we will have instead a rectangular array. So far we have seen that we have an array of arrays. We can have an array of arrays which is really an array of pointers or a pointer to pointers. We may wish to use pointers to pointers outside an array as well. Here is multiple indirection. So you can have a pointer point to another pointer that point to the target value. In single indirection, we are used to this. We have a value, a target value, and we can have a pointer to point to it. In the multiple indirection, we have a pointer that points to another pointer, which in turn points to the target value. So, in order to access the target value from within the first pointer, you apply the asterisk twice in order to get the value. Let's take an example. Here, let's consider x, a variable x, with the value 10. Let's draw x and let's put 10 inside it. And then let's consider a pointer to integer px and assign to it the address of x. So here is our px and px points to x. And another pointer, but what would be the pointer's type if it will point to px itself? Since px itself is of type int star, a pointer to int star will be int star star. We will call this pointer ref and we will assign to it the value of the address of px and not the address of x. So ref will be a variable. It will point to the variable px in the memory. We have seen this in the arrays of arrays, but now we are seeing it alone. We can change the value of x by either saying x equal that or this, or even through the pointer px by saying dereference px and put 20 here. Let's see the effect of this instruction. And now we have another way in order to put something in x through ref. So we will dereference ref twice, the first one to get into here, and then the second dereference to get into the x's value, and put 30. If we print x equal the value of x, now we will get 30. We go to the program and we can make sure that this gives us the value 30. As for the last section in this chapter, it is about void pointers. So let's see, what are void pointers? Void pointers. C supports the pointer to void type, which is denoted void star instead of, for example, int star or char star or float star or whatever star. Variables of this type are pointers to data of an unspecified type. It's as like saying, I have a pointer, but it can point anything, a wildcard, a joker. In this context, pointer acts as a universal type. A program can convert a pointer to any type of data, for example, an int star, a char star, etc., to a pointer to void. We can cast from int star to void star and back to the original type without losing information. So let's take an example to illustrate this new concept of void star, and I have this program for you that I will explain line by line. First, we declare two integers, x2 and x, and a int star, which is a pointer to integer base type, which is px. The same thing, I will change the types and I will declare y, y2 and py, which are two variables of type float and a pointer to a type float. And then I will declare this joker void star p. So here p can point to any variable of any type. It is a pointer, a universal pointer. I can make p point to x to have the address of x. To dereference p, we must first cast. So if I want, for example, to print the content of p, I want to tell the compiler that since p is a void star, cast p to int star and then dereference it. So this is printf %d, where %d is the dereference of p, but after casting p to int star. You can also say x2 receives the dereference of p after casting. And also, to assign a value of p to another pointer, suppose we want to copy the value, the address that is inside p to px, you can say px receives p, but you have also to cast first. Px is assigned the value of p, but after casting to int star. Why? Because px is of base type int. We can do the same thing in the same program, make p point now to another variable of different type. So in the same program, we can continue and say p now points to y, where y is a float. And I can repeat the same thing. I can copy from this pointer's value to another pointer's value. I can dereference, etc. and etc. So the effect of this program is first 2 to 2 because I have printed 3 times, and another time 2.1, 2.1, 2.1, which will show you that by comparison to the beginning of the program, there is nothing wrong, and this is a powerful tool in your hands to use void pointers on one condition: to know how to cast it. So this was about our chapter, pointers and arrays. We have seen pointer definition, pointer operations, and null pointers. We have introduced arrays and we have seen them as pointers because this is the reality. We compared C strings versus arrays of characters and we saw when to use each type. We know now that in function parameters, the C strings and the array of pointers are all pointers to pointers to characters. Inside function parameters, there are no really arrays that are copied from one function to another function. We have seen also arrays of pointers, which introduced also the multiple indirection, pointers to pointers, and we finally concluded that chapter by showing you what is void pointers. So next chapter will be about structure, and this will introduce the chapter which is after that, which concerns the dynamic allocation, so the allocation inside the heap and the linked list.